of the course. It's split in two. In the afternoon, I will discuss ignition in many cases for safety, for gas turbine, for rocket engines. And in the morning, I want to come back to this issue of large eddy simulation. Remember, I told you that we want codes which are non-dissipative, which are high order, to capture turbulence. The interesting thing is that as soon as we do that, we also capture certain features of turbulence. And certainly many of you in this room know about the famous butterfly effect, you know. Any butterfly in France flying and then the weather will change in India. Well, it's not happening this year apparently, but the point is that in a code, this has a direct effect. In an LES code, when it's a good code, and when it's not dissipative, any small change somewhere can create a big change in the flow. The small change, the first source for the small change is the mesh. If you have a bad mesh, things are not going to work. So what I want to do first is to illustrate that by talking about bifurcations. One of the things which happens when turbulence starts, kicking in and doing what it likes to do, which is, bifurcating, is that in your code, you will also start seeing bifurcations. What does that mean? That one day you will run your code, you'll have a result. The following day, you will change the processor numbers, and then you have another result. And they could be vastly different. So this is something you need to learn how to handle because it's a new problem. When you do once, you can run your once code anywhere. You always get the same result. It's not turbulent anyway, so there's no reason for it to bifurcate. In an LES code, it's different. So I'm going to start with this example, which is really a swirling flow. And that's a real story that we had a few years ago for this PhD. This guy was supposed to do two-phase reacting flows, and even when he never did more than non-reacting gaseous problems because we've faced this problem. So this is the story I want to tell you now. Now, we're going to be talking about swirling flows, and I don't think I've done that until now, so I'm going to do it here. The number you use to characterize swirl or swirling flows is this, what we call the S number, the swirl number. The swirl in a 3D flow, the flow field, of course, is a full 3D field. If you want to characterize it globally, what you do in one section, you measure, basically you measure u theta divided by u actual. So because it's the rotation divided by the actual velocity. Because you want it to integrate over the whole section here, you do the integral of that over a section and you quantify that by the flux also. So that's the flux of the tangential momentum divided by the flux of the actual momentum. This number is the number that everyone is using to characterize a swirl flow. And we know that when this number is large enough, then you start creating a zone of recirculation on the axis. And this is what we want for combustion. Now, here, there are many different topologies for this zone. One of the things which may happen if you go into this region where the swirl is large is that you can have the spiral mode, where this is the visualization of the axis of the vortex. Or you can also have the bubble mode. And interestingly, you can have both, for example, on the same wing. This is a V-shaped wing, the flow is coming from that side. On this side of the wing, you can have the spiral mode, and on the other side, you will have the bubble mode, and there are bifurcations between the two. Now, the issue here was to know, is LES able to capture these bifurcations, or are we going to see it in LES? And if it happens, which quality do we need in our solver in order to characterize that? So we're going to look at a special swirler, but what I'm going to say would be valid in any of these swirl flows. And you're going to do two things. First, I'm going to show you that these bifurcations do occur, and I will show you why. And second, I will explain how we try to master the problem of the mesh, because many of these things are going to be controlled by the mesh. So let me start now with this, the computation of this swirling flow. So for this swirling flow, actually, we're going to use two codes. AVBP is the code we use for fully compressible flow. And we also have a code called YELS2, which is coming from Rouen, another lab in France, which is dedicated to low Mach number flow. Apart from that, they're both high order codes. And you will see that sometimes when you don't really know what's going on, it's good to have two codes. Because if the two codes give you the same answer, then it tells you that probably it's the right answer. That's the geometry that we compute. So you can see here the passages for the swirling flow. There are two here. Well, actually three, actually. 1, 2, 3. You have here the global domain. And again, we compute the atmosphere around the whole system. So we mesh, like 1 meter here. And we know that the swirl in this system, because of the vanes design, is large. It's of the order of 0.7 or something like this. So we are going to define the place where we measure swirl. And it will be in this region here. This is the place when I will talk about swirl. We measured it at that place. Swirl is changing. The swirl that you have downstream and upstream of a given section is not the same because the flow is changing. So we used it at that position. So let me show you first the results right away. So this is the results of the cold flow LES. You get the student, you get the code, you tell him run it, and he comes back and he tells you, well, with AVBP, when we use the sigma model is a model which is a little bit better than Smagorinsky. And we get this result for the velocity field. That's a cut through the central axis of the swirler. And when we use dynamic Smagorinsky, we obtain this flow. You see the difference. This guy here is what we're going to call a blasted breakdown. So it's opening very much. When the flow gets out, it follows the walls, basically. This one is what we call an actual jet. There's still a jet, going straight. And just by changing only the subgrid scale model, you have a different result. Now, you look at the experimental data. Those are velocity profiles as a function of distance to the axis. And you see that it's a cut somewhere here. In the center, there's no velocity. And when you go in this region, you can find the bumps here. And you see that the blasted jet is like this. That's the LES. The actual jet is these curves here. And the experiment is here. So even so it's not perfect, it's telling you right away that this solution is not right. The blasted breakdown, this thing is not what the experiment is doing. The experiment is going straight. Experiment is doing something close to that. So we said, well, maybe we have a problem with the code. Let's change code. So you ask the student to take another code, and we run everything. So we did it with Yales then. And Yales said exactly the same thing. Yales with sigma gave the same result as AVBP. And Yales with dynamic Smagorinsky gave the same result as AVBP. So it is not a problem of time advancement or accuracy of the method. These two codes are completely different. So it's really telling you that there is something going on linked to the subgrid scale model. And so that's not such a good news, okay? Because it's telling you that you have a problem there. So the first thing we tried to do is to see if the swirl number was really the same in those two computations. The swirl number is not a boundary condition here. The swirl number is the result of the computation itself. When you look at these flows, the swirl number is measured here. It will depend on what's going on inside the swirler. In the swirler, you have the vanes. So if the flow, for example, is attached on the vanes or detached, you will have a different profile for the velocities. So we measured the swirl. And we found actually that our simulations could be separated in two categories. Simulations giving us a blasted jet here, which have a large swirl number, and simulation giving us an actual jet, which have a smaller swirl number. And it's the same simulation. You just change the LES model, and in one case you have a blasted jet and a large swirl number, and here you have a smaller one, which is telling us that maybe this is not the cause, but at least it's correlated to what's going on. We know that when you increase swirl, you open the jets, okay? So then we said, okay, we have to find a way to quantify that and to understand why this is happening that way. So there's something you can do experimentally, is to say if the swirl is the good control parameter, we could change this geometry, which is, as you can see, really complicated. The flow is coming here, passing through the swirlers and flowing outside. We could replace it by something else, which I'm going to show you now. We have stopped using this thing, and we have started the simulation after the blades. here, here, and here. There are 3 inlets, so that we can impose exactly the swirl we want. So in those sections, we're going to impose the velocity and the swirl, but the swirl will not be controlled by the real geometry. We will be controlling it, so we'll be able to change it the way we want. So that's what we call an adjustable swirler, where the simulation begins after the blades. That's a very clean environment, because now we can control the swirl the way we want by changing the amount of swirl we put in each inlet here. So just to make this clearer, it really means that in the first simulation I've shown you, the swirl was the result of the computation, because it's imposed by the geometry. Here, we will impose the swirl in all these sections, so we will be able to change it. This way, we're going to be able to see if the swirl is the parameter which controls the topology. And so when we did that, that's one set of computation. We changed the swirl the way we want now. And you see indeed that at the swirl number of 0.79, the jet suddenly goes from actual jet to a blasted jet. So this confirms that there is a transition somewhere. And if your code goes one way or another, you find one position or another position. Now, when you do that, the other thing you can do also is you can slowly increase the swirl. One direction to go there, or slowly decrease the swirl in one direction and go there. And then you start having to talk about hysteresis. These flows can be stuck on one regime and then they go to another one. For example, here, if you start from a low swirl value when you have an actual jet and you increase the swirl, you will go to this point. So I'm here, I'm increasing the swirl, I'm going here. But now if I decrease swirl back to this point, well, I'm staying on this position. And I have to decrease it much more to be able to go back to this position. So this flow has a memory, if you want. And we see that actually in flames too. I will show you examples later. So really this hysteresis loop is happening in the real world, and it's happening also in the simulation. Now, the interesting question now is, why do we have that? Why is this happening this way? Why is swirl changing also when you do the simulation? And this is due only, remember, to the impact of the subgrid scale model. In combustion, we don't talk much about subgrid scale model for the dynamic part, for the velocity. But you see here that we need to start talking about it. Well, the thing we did is to start looking at the simulation itself and at the details of the simulation. So for example, you start looking at the turbulent viscosity. This is the viscosity ratio. So this is the ratio of the turbulent viscosity divided by the laminar viscosity. So it's this quantity. You know that this ratio should be small. In ones, it's of the order of 500 to 1,000. Here, it's 80, which is a reasonable number. But you see that when you use dynamic Smagorinsky, on this cylinder here, the level of nu t is much higher than the level of nu t here. Okay? So it's telling you that there's something big happening for the turbulent viscosity. When we change from dynamic Smagorinsky to sigma, there are big things happening on the turbulent viscosity and on the flow itself. Now, why is that so? Well, if you look at the flow itself, we know that the flow has to depend on the turbulent viscosity. And then you have to ask yourself the question, how do you compute turbulent viscosity? Well, in the k-epsilon model, viscosity is the ratio of k squared over epsilon. So those are quantities that you resolve which do not depend on the grid. In LES, nu t is a function of delta. You know that the Smagorinsky model says that at every point, the turbulent viscosity is a constant multiplied by delta square, the square of the size of the mesh multiplied by Sij square, which is the gradient, the velocity tensor. So really what this means is that the turbulent viscosity is a strong function of the size of the mesh, very strong, so that the flow itself is a very strong function of the size of the mesh. In other words, the size of the mesh is the most important thing. And when you talk to students who have done a lot, or even to advisors who have looked at a lot of LES, they will tell you that there are only 3 important things for an LES: the mesh, and the mesh. Once you get the right mesh, normally everything goes well. So it really proves that, what's important is to work on the mesh quality. So we went back actually to the simulation and we said, okay, what's happening if we change the mesh? Let's make the mesh a little bit better. For example, we knew that in those zones here close to the swirler, we didn't have that many points. So we made a better mesh with more points, and we rerun the simulation. And when we do that, suddenly, independently now of the subgrid scale model, you get the same results. Okay? Which is really telling you that, of course, there is an effect of the subgrid scale model, but this effect appears only if the mesh is not right. If the mesh is right, then most models, will do a good job. But as soon as the mesh is not right, you go into problems. So the conclusion then at that point, after that was about a year, we still had to do combustion, but we said, okay, let's give up on that. Let's work on the mesh, because obviously the quality of the mesh is something we need to work on. Now, that leads me to the second part here, which is how can you be better for the mesh? In a one's computation, normally you don't really care about the mesh. Okay, you can have a bad mesh, you can have strange, elongated elements, changes of volumes from one mesh to another. It's not that bad because what you try to do is to have a grid-independent solution. And the mesh does not play a big role there as soon as you are sufficient resolution. For LES, the picture is very different. So let me just explain how these things are done today. And I've seen actually some of you doing these things. And it is true that you meet someone and the guy is telling you, I'm using this code with this subgrid scale model and it's not working. And then you have to say, okay, this is not really important. The problem is which mesh do you use? Well, the mesh, it's this mesh, and doesn't really care, how the mesh was done. But actually, that's the most important part, because the meshes are usually written by someone, and they are written just by intuition. If you look at the meshes you've done, no one told you where to put points. You felt, okay, the flame will be here. There is a wall. I'm going to put more points. But did you put enough, or did you put them at the right point? So that's the first problem in LES today, is the arbitrariness in the way we built the mesh. And this is actually much stronger than all the rest. This is the point where you need to focus. So in industry, when you would do that, and I'm surprised actually that industry has not seen that yet. Industry, people would have identified for a long time that this was the critical part, and they would have set up procedures. Actually, when AVBP is used now at Safran, they have a procedure for that. They have a manual which says exactly where you should put the points, where they believe you should put the points. Ultimately, when you buy, this guy was Italian, so he was making advertisement for Ferrari, but the idea is that when you buy an LES, you don't want the LES made with mesh A, B, C, or D. When you buy an LES, you want a good LES. So when you buy a car, you want a good car. It should not depend on who built the car. It's the same way to do LES, it should not depend on the guy who made the mesh. And unfortunately, I've just shown you that it is dependent a lot on the guy who made the mesh, because you change the mesh, you get another result. So that leads to a point which is now obvious for LES, is that you need a procedure which will give you the right mesh. So that seems easy to say, because a lot of people have done it in the past. For example, this is an aircraft here. We're looking at a wave, or either for acoustics or for shock waves. And then you know that you can add points, you can remove points in certain places and add points at other places. And if you do a shock wave on a plane, it's pretty clear that you're going to put a lot of points here and not many points here, because you know where the shock is. The main problem when you go to LES is that you're going to need to put points where vortices are, but there are vortices everywhere. In a turbulent flow, in a combustion chamber, you take a piston engine, for example, there is vorticity everywhere. So you cannot really say as easily as here, my mesh refinement system needs to put points here. Why here? You know, everywhere where there is turbulent activity, you should put points. So how do you decide? This is where things become complicated. The first thing to say is that the decision can be made on two types of criteria. You can do it what we call dynamically, or you can do it in a static way. Dynamically, it really means that you're going to follow. This is, for example, a vortex here propagating in a stagnant flow. You see the mesh here, and you see the mesh is obviously following this thing. So at each time step, or maybe every 10 time step, you stop, you look at the flow, and you say, okay, I want points here. I'm removing points here, moving them here. I do an interpolation, I restart the code, and I go to the next time step. This is dynamic meshing. We do that in Yells too. We don't do it in AVBP. One of the reasons we don't do it for turbulent flows in most cases is that here there's one eddy. But if there were thousands of eddies, you don't really know what to do. So we felt that the more reliable way to do that was to look only at the mean solution. So we run the code like for half an hour, real time. Then we stop. We look at the mean solution. And using only the time average flow field, we try to guess where our points should be. And that's, of course, much cheaper than that. You must realize also that doing that on a parallel machine is very difficult. If you start modifying the mesh every time step, you have also to care about load balancing every time step. Because if the basis of dynamic load balancing is that each processor must have exactly the same load, which really means, in general, the same number of points. But now suppose that this processor here takes care of a zone where you need more points, so you're going to have more points here. And here, this one is a quiet zone, so it doesn't need points. So now the number of points here will be more than that one, and the load balancing will be destroyed. Which really means that if you want to do dynamic load balancing, you need to redistribute all your points between processors every time you do that. And that's a lot of communication, a lot of reorganization. And also you need to rerun the mesh generator every time step. Or you need to carry with you a methodology which can move the points of your grid without going back to ISEM or Centaur or ANSYS mesh. And that's very expensive to do. So for the moment, we didn't do that in AVBP, and I'm going to show you what we did. We always take the LES solution. Yeah, we take the LES solution. So, as I said, there are too many vortices here to track them one by one. You look here at this simulation, you can see, you're not going to try to capture each vortex here. I mean, it's just going to be too much. And as I said, the polarization is a big issue. If you don't want to have a lot of work in terms of load balancing, you should start with the mean flow. So we'll use only mesh adaptation based on the mean flow. How do you do that now? There are two. First, you need a new code. Okay? You need a code, which here is a code coming from INRIA, and it's called MMG3D. Those are codes which handle only mesh. Okay? So what you give to this code is a mesh, and then you give it a metric. The metric is a function which you believe is the important function that should be optimized. Then with this mesh, so the input of a code like this looks like this. You take the mesh, and you add a metric. And the metric is usually a 3D field on the same flow, which has, gradients, etc. And MMG3D, this code will look at this mesh, look at this flow field and tell you, okay, you have big gradients here. I'm going to move the mesh to be better here. And it's moving the mesh according to the metric. The metric gives weight to the points here. And you're going to put these two things together, you will end up with a mesh which will, look like this. It will be refined at the points where the metric was large. that doesn't tell you how to choose the metric. It's just telling you that you combine these two things, you give him the mesh you had, you give him a metric, it will give you a new optimized mesh so that you capture this metric better. So this is what's done here. So we'll run the code for, as I said, a few flow-through times, a few milliseconds, then we stop. We take the mean solution, we construct a metric. I will describe this metric in 2 seconds. Then you go to MMG3D, and that creates a new mesh. And then with this new mesh, you can continue the simulation. You can actually, after a few flow-through times, start it again. But in most cases, you do it once, and it's sufficient. So this way, we have full control of the mesh, and we can adjust it the way we want. The problem now is to define the metric. What is important if you have a mesh for LES? That's actually an interesting question. You know, if you would want to use your intuition, many of you are computing swirling flow, you know, like this, for example. Suppose there is no flame, because when there is a flame, intuition tells us that we should have points in the flame. But if there is no flame, where should we put the points? Well, that's not clear.
For a particular cell, it only looks at the gradient, or it looks at the entire flow field and then choose the...
It's the entire flow field. I'm going to show you what it is. Typically, a gradient of velocity, for example. That's a local quantity, but you compute it over the whole domain. So if you think about non-reacting flow here, for example, there are many things that could be a good metric. One of them could be the turbulent viscosity. Some of you actually have shown me some results, you know, by using the Pope's criterion, where you try to quantify how much energy is resolved, how much energy is not resolved. So the Pope criterion could be a good metric. But it could be also the distance between the wall and the first point, the y plus. Or it could be the vorticity. It could be anything. So the problem is, which one do you want? And which one is good? Well, this is where you have many choices. Yeah, yeah. Yeah, that's the problem with this methodology. Well, maybe not a lot of time, but some time. Yeah, you need to run this thing for a certain time before you can do this procedure. Yeah, it's not a dynamic procedure. But in most cases, these simulations take, you know, a few days, so it's easy to plug it in. So what about the metric? You can imagine many metrics. For example, that's the Pope criterion, actually. This is the U prime field. So that's the resolved turbulent kinetic energy. You don't want to see in your simulation a point here which has 0 kinetic energy, and the next one will have a very large kinetic energy. Probably this means that you have missed here something, and you should add points. You have the same information almost on the gradient of the mean velocity. If it is unresolved, you're not doing a good job. You have the wall distance, and then you can also mix these things. And when you build your metric, this is what's going to decide on what's going to happen to your flow later, to your mesh. So choosing the metric here is the big issue in this problem. So let me show you a few examples, but the important thing to say is that for the moment, there is no global error estimates for LES. People use the Pope criterion, but my experience is that the Pope criterion can tell you the mesh is good, and in practice, it's not good. And also, the Pope criterion works only for non-reacting flows. So if you go to combustion, it's another topic. I'm not going to talk about combustion because for the moment, we don't know how to do that with combustion in the right way. We do it only for cold flow. So just to remind you where we are, why we do that is because we want a systematic method to avoid this kind of surprises. And how we do it by running the LES solver for a few milliseconds, going to the metric generator, going to the MMG3D code, and then doing it again. That's the global idea of this thing. OK, so let me show you a few test cases. That's a usual test case, actually, which is a good one if you do LES. It's called the Dellenbach swirl case. It's just a cylindrical duct connected to another duct. And here, the flow can be swirling or not swirling. And they have measured the velocities and the unsteady velocities, so you can use it as a good comparison. And then after that, we do this without swirl and with swirl, and then we go to the swirler that I showed you when we started this talk. OK, so this is an example of the actual. So in that case, there's no swirl, so it's a simple jet in a box which is typical also of combustion chambers. You know, you have a dump here, so you could have recirculated gases here. So this is the instantaneous velocity. You recognize it is LES because it's moving. You know, you have vortices. And this is the mean flow. And we have measurements at different stations here. And we can look also, for example, here at the turbulence intensity. Now remember, we run this thing for a few milliseconds, then we take averages. We have these average fields, and you try to build a metric on them. If you build the metric on the gradient of velocity, and if this is the homogeneous, the first mesh you still have to do yourself, okay? Because, so we did it homogeneous, same number of points everywhere. So if we use the gradient of velocity and go through this procedure, this is the mesh we obtain. The mesh manipulation code decided that there were too many points here and not enough here. So it's clustering the points in the regions where you have a gradient of velocity. If you do that on the kinetic energy, it's putting the points but not at the same place. Why is that so? In this region here, there's not much turbulent kinetic energy. The vortices are only starting to form, and the important part of the vorticity will be here, so the code will try to put points there. And you can also make a mix of these two. You can say, I want to have a good resolution of the gradient of velocity and of u prime. In that case, you obtain this mesh, which is like a combination of these two meshes. And when you... Okay, here the number of points is constant. Okay, so the cost is constant. This is a constant cost exercise. You can also decide that you allow the code to add points, but for the moment, it's constant number of points. So it's almost constant cost. And it's a really important point. When you think about industrial applications of LES, when I told you, we talk about €1,000,000 every year. If you can, at constant cost, optimize your solution, you're going to save a lot of money. Instead of doing a stupid computation, you do the right one right away. So this procedure is really of interest in industrial context. So if you look at the profiles now, you see that here you have the experiments, which are here, and here you have the different results, the homogeneous case, and you see actually that depending on where you are able to improve, the results by a large amount when you start using this kind of systems. And the trick is also, the difficulty is, why does it improve the quality of the result? Well, because in that case, it's adding points in the zones where you have vortices. Even so, we did not look at instantaneous fields. The mean flow fields actually correspond to the places where you have vorticity. So we've been basically adding points in the zones where you create eddies, which makes a lot of sense, We know that this is the place where things are happening. So let me go back now to this guy. Yeah.
The slide where you're comparing the results with the...
Yes. Well, before.
Why are the results improving as you go along, have higher expediting?
At higher x over d, why?
You see from 4 to 10 it is like improving. The K is actually having a better match.
Well, the only thing we say here is that the optimized solution is better than the non-optimized one. Even so, it's not perfect, okay? We miss a little bit of velocity here.
If you see, at least the K is constantly improving from 4 to 10.
Yeah. From 4 to 10. Well, at 4, basically everyone agrees, okay? That's the easy case. The difficulty is to go to larger values here. Let me show you the swirl case. The Dellenbach, the actual case is probably the case where the mesh refinement does not change things so much. Let me show you this guy, Here, that was the case where we had this big problem with the blasted jet, and this is the actual jet. So here we also applied mesh refinement. Before we did that, we looked a little bit at the flow itself. And here we plotted the sigma model and the dynamic Smagorinsky model. And you see that the topology of the flow in the swirled region, in the passages, is very different. In certain cases, you have separation. Here, this is a zone of separated flow. And in other cases, you don't. So it's really telling you that the mesh here is going to be very important, but how do you decide in the metric, in the swirl flow, how you construct the mesh? And that's an open question. So we tried different things. And what we felt was important here is near wall resolution. So it's not really the edges, it's you need enough points near the wall. And if you use certain sensor, you end up with another problem, is that this methodology should not bring all the points at one place. For example, near the wall. That's the limitation of a methodology like this, is that it's easy to conclude that you should put all your points in the boundary layer here. And so you would cluster all of them here, and here you would have nothing. You have to limit that because otherwise all the points will be at the wall. So we tried different tests for that, and the main idea which actually seemed to work is this one, is to say we should have reasonably regular mesh near the walls. And that's, we had long discussion with the PhD student about that. His point was to say, if you have two passages, the important thing in the swirler computation is the flow split between these two passages. Because if one computation you have 50-50 and in another one you have 80-20, of course the flow will be completely different. So you should at least try to have the right flow split. The flow split depends on the pressure losses. Okay, if you can imagine a swirler is actually a system where the flow is arriving like this, and here it can follow one path or another one. And it will go, it will split according to the pressure losses. If you block this one, everyone will go to 1. If you block the other one, everyone will go to 2. So the pressure losses in 1 and 2 should somehow be coherent if you want the right flow split. The way to do that is, even if you make mistakes on the pressure losses, you should make the same mistake on both sides. That was the key problem there. And so that the split remains the same. How do you get the same mistakes? Well, you should have the same y plus. All the points here, out every passage, should have the same value of y plus at the first point. Not a very small value, but the same. You see right away where the metric begins to be important, because that's a strong statement that you just need the same values of y plus. So this is what was done here. So this is the basic mesh, the one you've seen before. We ran it. And then we said we want the same y plus at the wall. So the mesh points moved, We went from here to there, and you can see that we clustered points at the walls, at all walls here. And if you go along these walls, you will see that the y plus is almost constant on all these sections. And you see also that to do that, you have removed points here at different places, because according to this criterion, they were not important. So that when we look now at the PDF of y plus, that's the initial PDF, and it was a wide one, and you see that with the new one, it's much more centered, and so all the points are around this value of y plus, which is of the order, of the target we wanted to have. It's not 1, it's much more than that. We are probably of the order of 50 to 100. Now for this flow, the results were spectacular, because the flow moved from that point to this one. Okay, this is the experiment. This is the initial mesh, and this is the adapted mesh. And you see that in terms of velocity, axial and tangential, the results are very, very different, and they are actually much better when you go to the adapted mesh. So in that case, for the same cost, the results were really improved. Now, just a point also that few people discuss. I've shown you LES, and I've told you that when we compute flows, swirl flows with LES, we do normally extremely well for the velocity fields. What I didn't tell you is that you normally do not well at all for pressure losses. Okay, so that's a problem that we investigate and that most people don't discuss. Well, we've been discussing with Siemens for a while, for example, but you have a swirler here. If you measure the velocity fields here, and you compare them to LES, normally you're doing reasonably well. I mean, I can say you're doing really well. But if you just now compute P2 minus P1, which is the pressure loss in this system. And Professor Kouchaoui told you that this thing should never be more than a few percent of the mean pressure, because otherwise the engine is not going to be efficient. Well, we have mistakes of the order of 30 to 40%. And once does not. Okay? Once is doing well there. So once basically is giving you the right pressure loss with very bad velocity profiles, and LES is doing the opposite. Doesn't make sense. Okay? Now we know why this is so, because we've been able to fix this problem. It's really related to mesh. You can see here the first step of that. When we go from the original mesh to the adapted mesh, the error drops from 100% to 70. And now if you go to another model, it drops to 40. And now when we've been able, now we have worked a little bit more on this problem, we have found a different metric, now we are back to 2%. And so it really tells you that in the swirler, in the passages here, mesh resolution does everything. And if you don't have a good mesh resolution, you won't have a good pressure loss. Okay.
So, have you ever tried running LES on diffuser basis? Were you able to predict the pressure loss?
Not on diffusers. Diffusers are tough, because you get separation. Well, it depends. If you have separation, then it's really the outlet boundary condition which you need to work on. We didn't do it on diffusers. But that would be an interesting one, yeah.
So the pressure loss that you're not seeing in LES but they're getting in graphs, is it only because of mesh, or the models, LES models which are near the wall are not as good as the correlations we have for RANs?
That's the second point. The correlations for RANs have been tuned over years, and they're doing better in the passages here. Then when you go into the free flow, then RANs is completely gone. But here, for pressure loss, they're doing well. And the only way for LES to catch up is to have a good mesh here, because LES does not have all these tunings, all these near wall corrections that you have in RANs. You have tens of corrections. They have been tuned over the years, and this is why they do reasonably well in terms of pressure losses. But then I've shown you that yesterday or the day before. Here in the flow itself, it's not as good. But still, you cannot go and tell people, I have a wonderful LES code, but I have a 40% error on the pressure loss. I mean, I'm going to say it's not reasonable. So that's a major problem now. Yeah.
Did you try in between of the waves? Did you try with RANs, and then the other mainstream? Did you try with LES so that you can match the pressure drops as well as velocity, right?
No, we haven't done that. Yeah, you could imagine mixing the codes, but in most cases we don't want to run RANs anyway, so we don't touch RANs. DS is actually going in the same direction. DS is trying to resolve the wall, okay? It's a way to resolve the wall, but DS in a swirler is really difficult, okay? Because you don't know what is close to the wall and what is far from the wall. Yeah, well, the problem in the topology of these flows is really complicated. And for example, if you look at a swirler like that, what is close to the wall, is that if you have a separation here, how do you do it, okay? But it's true that when we say we try to optimize Y plus at the wall, it's not very far from what you would do in DS, It's saying at the wall, I want some kind of wall treatment. And you can do it with DS or you can do it with LES. My opinion is that we use DES a lot for aircraft, because in an aircraft, I know what the near wall is. In a flow like this, it's kind of difficult, You would have to draw a line here saying, okay, this is DES, this is LES, and that's tough. But sure, it's another method that you can use there.
The adaptive machining is shown was
Yeah.
mostly done by velocity gradients or like some other. So you said the pressure drops are it's difficult to capture. Has anything else been tried to refine the machine and so that?
Okay, that's not something which has been published yet, but we know now how to do that. We know that if you're worried about pressure loss, you can write an equation for pressure loss. The equation is a bit complicated, but it looks like this. You take the momentum equation and you derive it, and you end up with the volume flow rate multiplied by P1, well, P1 plus rho U1 square, which is the minus P2 plus rho 2 U2 square, which is the pressure loss between the two sides. This thing is equal to the integral of the epsilon dV. That's the first. There are other terms, but the main term is this one, where epsilon is the dissipation. It's nu dui dxj square. And so the metric that you should use is epsilon. If you want the right pressure losses, COE tells you that the field which must be resolved is the field of dissipation. And dissipation can be computed from the LES, and when we put points at the places where dissipation has strong gradients, then we get to 2%, 3% for the pressure loss. And the velocity field still remains very good. So it's really a good example that everything was in the mesh. If you can get the right mesh, then you get everything right. If you get a mesh which you built, then it's not working. Again, it's nice because it's telling you that COE is useful. This thing tells you where to put the points if you're interested in pressure losses.
Do you think is there any specific reason as to why it's not just velocity pressure? The species would also be, or do you think some meshing has to be done based on species variance?
Well, for the moment, I didn't talk about species, okay? There's no combustion here, no mixing, no nothing. It's only flow. And for the flow, what it's telling you is that pressure or velocity or vorticity, none of this is important as this quantity, as important. This quantity is what creates the pressure losses. You know, it's exactly the same thing if you would like to compute a flame. COE will tell you if you want to compute a flame right, what you need to optimize is not temperature or velocity, it's heat release. It's the reaction rate, because reaction rate does everything. Once you have the reaction rate in the flame, you have all the rest, because it's the source. All the rest is the integral of that. It's the same thing here. If you have epsilon, then you will get the rest right.
So this Smolensky subgrid model is known to have issues near the wall. So there's one other subgrid scale model, WALE, WALE, that is, they claim to be good near the wall. Have you ever tried that?
No, we like the subgrid scale model to have a limited effect. Actually, we see that the subgrid scale model has a big effect when the mesh is bad. When the mesh is good, the subgrid scale model has much less effect. So that's the region where we'd like to be, okay? Because otherwise, that's too many things at the same time.
Because I actually tried that and compared, I was getting a better velocity profile as compared to Smolensky.
Yeah. I agree. I mean, that's the problem. That's when you change all these things at the same time, it's difficult to find your way. This is why we need a guideline here. We need something to tell us, yes, your grid is good, or no, your grid's not adapted to this flow.
So in any combustor, any geometry, when you do the aliasing, the meshing it follows some critical grid size. So the grid size is maintained through the Z axis or throughout all 3 dimensions?
That's the question, yeah. You don't know that when you start, okay? First, if you haven't done the computation, you need to do a first computation to see where you are. But then afterwards, in a flow, you know, whatever the flow is, for LES, you don't know where the mesh points should be. If you do an aircraft, you know that everything is taking place at the walls here, so you put points near the wall. But in a combustion chamber, it's happening all over the place. So if you look at, you know, I think I've shown you this, these movies here when we looked at the flow in a turbulent combustion chamber, and you see vortices everywhere. So before you have done the LES, you cannot know where to put points. That's unfortunately the status. I must say also that what I've shown you here is for non-reacting conditions. If you do combustion, then you're on your own again. For example, also if you do mixing, we know that it's a usual problem when we compute this. I will talk about them in a few minutes probably. When you compute the flows for Siemens, and they use pilot flames, we know that for pilot flames, everything is controlled, not everything, but a lot of things are controlled by the zone where you have here, this is not this case, it's a similar case, but here you have the pilot flames, and it's a very small jet, and this jet mixes with air. If you don't put points here where the mixing takes place, then it's gone, it's finished. So that really means that you need, probably we need to do criteria for non-reacting flows, but then if you go to combustion, we need to think about mixing first, because if mixing is wrong, it's not going to work, and then we can talk about reaction zones. And this is a big topic. I think it's going to be a big topic in the future, because now we need to be able to adjust the mesh. This is why also I've talked to some of you here about HP method. You know, the new codes which are coming out now, I said about spectral differences and discontinuous Galerkin methods. These methods have a great capacity because they can increase the resolution locally by increasing either the precision, which means decreasing h, which is the size of the mesh, or increasing the order of the solution. In other words, you can, with this method, decide that here, mixing is important, so I'm going to use a method which is 6th order or 8th order in space. And then here it's not important, so I'm going to use a 2nd order method. This is one of the possibilities of this method, which is to adjust locally the precision by 2 ways, small mesh or high precision. And in the future, we're going to need to have all these things coupled to the LES. We cannot do LES in a blind way as far as the mesh is concerned. You cannot just hope to put a mesh and let the code run and, you know, hope for the best. It's not going to work. We need to control the mesh. Of course, if you put 5 billion points, maybe, you know, you can go for that, but that's not going to happen, because we know that very big meshes everywhere is just going to be too expensive. So we need to, you know, save a little bit of money there.
Just like in this geometry, the flow is, let's say the flow is along H direction.
Yeah, flow is like this, yeah.
So we try to maintain the size of the mesh along the H direction, and try to have a little grid, the grid size more than that LES along the Y and Z direction. How is the result effect? Will it differ drastically? I mean,
Yeah. Every time you change the mesh in LES, first, every time you change the mesh in LES, you change the results. That's built in, okay? Because the dissipation in an LES code is a function of delta square. So every time you change the mesh, you change the results, the instantaneous results. I will show that actually in 5 minutes here. Then the only thing you can hope is that these things converge. So the mean solution should be the same, but the instantaneous flow will be different. Now, the big question is that once you have run the solution and averaged everything, do you have something which is resolved enough? And that's where you need to do more than just put points, you know, by intuition. You need criteria. The Pope's criterion was the first one, but as I've shown you, there are many others, you know, that you should look at when you do an LES. I would also like to repeat that the first thing you should do when you do an LES is to make a movie and check that it's moving. Because if it's not moving, it's not an LES. Okay? Actually, this criterion is almost similar to the Pope's criterion. Huh? If you make a movie of an LES and it's not moving, the Pope criterion will tell you none of the energy is resolved. You know, everything is subgrid. So, but the movie is really the best thing you have to do when you do LES. Look at the instantaneous flow fields. So let's continue now by discussing something similar to what I just shown you, the fact that the flow can bifurcate because of different problems. Now I want to do the same thing with combustion. And so that's bifurcation now with combustion. And we know that when you do a numerical study or an experimental study, you would like the flow in a combustion chamber to depend on a limited number of parameters. For example, if you specify the flow rate and the temperature and of the fuel, and same thing for the air, and probably also you control the level of water in the air, and then normally you will have one flame. Okay? We know that in practice it's difficult to do in an experiment because the atmospheric pressure will change the density. We know that the temperature of the chamber will go up or down, which is an additional parameter. You can have leaks. The composition of the gas might be different if it's not the same day. But even if we forget about all these parameters and assume that we have exactly the same parameters, we can still have problems. What I would call problems is that even if you control all the input parameters, the flame might have what we call different states. I will show you examples here. A striking one is what's happening for the Ansaldo gas turbines. When you start an Ansaldo gas turbine, certain of them, you start it, and then you have what they call a waiting period of a few minutes. And after this period, suddenly the flame changes shape, and then you can go to full power. If you try to go to full power right away, then this thing does not work. If you try to do that, if you go to full power right away, then the instabilities will be too much. What it's telling you is that this transition from one state to another is necessary to reach full power. Another way to say the same thing is that at this point here, there are two flames which are possible, and you need to be on one of these states to go to full power. So we know that these things are observed even without combustion. I've shown you before a case where the transition was caused by the numerical method. Now this is an experiment, a very simple one here, by a guy called Van der Schot here. That's a famous experiment because he showed actually this problem. There's an axis here of rotation, and here you inject the air, there's no combustion, and it's turning, okay? So you can then change the level of swirl, and this is what they've done. They started with a swirl equals 0, so in that case you have a jet. Okay, simple. Then you increase the swirl a little bit to 0.3, and you see that the jet starts opening, and when you go to 0.4, you start creating a recirculated zone here. And then you keep increasing the swirl, and then you start seeing this big recirculation zone that we like in combustion, which is here. And you go to 0.9, and when you are at 0.9, what you do is that you decrease again. You go back to 0.56, to 0.5, and to 0. And then the striking result is that this is the picture you obtain when you increase the swirl. This is the picture you obtain when you decrease the swirl. It's not the same. It's the same swirl, it's not the same flow. So you have two states, okay? This is the typical bifurcation that you can plot that way. If you increase the swirl, you go through different states, but when you go back, you go through other states. And that's of course a major problem for practical applications because you don't know when you start your engine on which state you will be, and that's bad. So if you go now to a gas turbine, this is an Ansaldo gas turbine installed in a chamber in Italy, and of course you've seen that, we've talked about it before. You have a precessing vortex core in this system, and I'm going to show you that this precessing vortex core, as always, is the source of various problems. So the target configuration, you've seen it already. That's the classical power generation system derived by Siemens and then sold to Ansaldo. We're looking at one chamber here. This is the mesh that we use for one sector. And this is the famous system where we have all these things working at the same time. Injection of air by the diagonal swirler, by the actual swirler, and then we have fuel. And this is a case where we inject fuel, which is methane, here, and you also here using the pilot flames. So the exercise I want to do with you now is show you this test case. This is operating point 1. You don't need to know what this is, okay? This is a point where the flame is attached here to the burner. And it's also attached to the lips here of the dump plane. We wanted to go to another point, which I will call operating point 2. Operating point 2 has a different inlet temperature, a different pressure, and a different flow rate. It's more powerful by maybe 20%. And when we do that in the LES, what's happening is that this zone here quenches. You see it's here, it's gone. It's only stabilized on the side. The student who did it in the LES changed everything at the same time, boom, and then we went to that point here. So we told him, why don't you do it more slowly? First thing is, before you go to that point here, put more fuel in the pilot flames. Remember, the pilot flames if you have a flame which has problem of instabilities, you can use what you had in the old cars, you know, starter. What is a starter? Give me more fuel. Okay, you give more fuel. Usually, the flame gets more stable. So if we start by putting more fuel here to keep the flame there, then we go to a new flow rate, a new pressure, and then we bring back the fuel flow rate to what it was before. So we come back to the same point, and we're able to do it, and then we get this flame again, and this one is stabilized. Which really means now that these two states, which are two flames, correspond to the same conditions and two different flames. And that's probably also what's happening in the on-site gas turbines. When you ignite the system, it's like this, and at some point, whoop, the flame comes here, and then you can go to a high power. Now, what we of course observed here is that this flame is bistable, and the interesting point is how do you go from one to the other? And the other point we wanted to look at is does it make a difference for combustion instabilities? We suspect, of course, that the flame transfer function of this guy is not the same as the flame transfer function of that guy. But still, when you're in front of the experiment, you have chosen the regime, you don't know that you have two cases. So that's a disturbing observation. If you make a cut here, and you start looking, you know, at the detail of the flow field, of course, the attached case is a flame which comes back here, and it's stabilized on the pure fuel that you inject here, while the other guy is, you know, nothing's burning here, which is easy to understand somehow, because in this region now, everything is cold. There is no reason for combustion to start. If there is a flame, it will stay there. But if there is no flame, there is no reason for the flame to begin here. And so you can really have two states. And if you look, of course, at the flow fields, they are very different. When it's attached, you have a strong acceleration here. When it's detached, there is no recirculation zone here. The flame is starting much more downstream. And you can make cuts in these flames at different points and compare the case, which is the attached flame here, to the detached flame. For the attached flame, for these cuts, for example, which is here, very close to the burner, of course, here you have hot gases here for the attached flame, and you have nothing for the detached flame, and you know, this keeps going as you go into the chamber. So this is temperature. This is the actual velocity, same problem. Recirculation zone in one case, no recirculation zone in the other case. And when you look at the turbulent kinetic energy, you see also something which I will describe again later, is that the attached flame is much more stable than the detached flame. The detached flame has a lot of turbulence going on here, and you will actually see that this is because it has a very strong PVC. While for the attached flame, because the burn gases come back to the inlet, the flow is more viscous and the PVC just disappears. So this is the kinetic energy, and you can see here the big differences between these two regimes here. Okay, even the RMS temperature profiles are different. Again, here you see very strong pulsation for temperature when the flame is attached, because there is a flame, the other one there's no flame. So all the fluctuations are different, and certainly the NOx would also be different. So why is it so? Well, it's easy. If you visualize now again a Q criterion or the low pressure, you see here for the attached case, using the same levels for the two, there is no PVC here, and here there is a PVC. And remember what I told you, it's like a competition between these two things. There's the flame and there's the PVC. If you're here, the PVC is moving the flow a lot, and so it's difficult for the flame to, to go back. But if the flame somehow is able to come here, then because it's viscous, then it kills the PVC. So you see the balance between these two phenomena. So when we've done that, the first thing we did, because this was really a study on thermoacoustics, is that we measured the flame transfer functions of these two things. So we sent acoustic waves here, using the methodology I have described before, and we did a few frequencies. When you do such a big gas turbine, you do them one by one. So you force at frequency F1, you measure then you do F2, then we did 4 frequencies like this. And the reference point where we use the velocity is this one. Yeah.
What I observed is different at the compared to the system when it gets unstable on its own.
Okay, when you do that, the engine should be stable. That means you have to use non-reflecting boundary conditions at the outlet, because if it is already unstable, it's very difficult to excite it. It's just not possible. If it is unstable on its own, you have to stabilize it before you can do the forcing. That's just the way it is. So that's what I've described also 3 days ago. You have to cut the loop, you know. You have to stop the resonant loop somehow. It's just, otherwise the forcing will interact with the self-excited mode, and it will be messy. So you really need to control this mode before you excite. Well, stabilization in a Siemens burner, in most cases, if you open the outlet acoustically, if you use a good NSCBC condition, it should be stable.
There are multiple surrounding forces.
Yeah. Well, the idea is that this thing and this thing, everything comes from the plenum. So when we force exactly the same way, this and that. Okay, we impose 5 or 10% pulsation here and here, same way. But actually, this one does not play a big role. It's really most of the air is coming through that side, and this is the one which has the strongest influence. So when we force, we measure the velocity fluctuations normalized by the mean velocity, and then we measure the oscillations of the heat release normalized by the mean heat release. And this gives us the flame transfer function. Then we can plot n and tau. So let me say this, you've seen already. So this is the forcing of the flame at small amplitudes. He wants to show this film. Okay, you've seen it already. Huh? That's a film which is just showing that the equivalence ratio in the chamber is not constant. Okay, you have mixing issues here. These jets merge, and when the premixed gases enter the chamber, they are not fully perfectly premixed, which means that that will change the response of the flame. So now we are forcing the detached flame at small amplitudes. So you see here the waves coming in because this thing is oscillating, and you have here the PVC, and you see that this flame, when you do a small amplitude, you don't see the amplitude so well. So you will need to do some FFT after that to recover the exact signal that you're sending here. And you can do that for the attached flame or for the detached flame. So here you have the attached case where you pulse the inlet, and here you have the detached case where you pulse the inlet. The pulsation, you can see it here. This wave here, it's not very strong. You don't want to make it too strong because then you're not in the linear regime. You don't want to make it too small because you don't see it. So you have to find a good compromise for that. But that's not so difficult to do. And you can obtain the flame transfer functions. And as expected, you see the gain of the detached flame is very large. So when the flame is detached, it's very sensitive to forcing. If you send a perturbation on the detached flame, it's going to react very, very strongly, which is bad for stability. On the other hand, the attached flame has much less gain. If the flame would have 0 gain, it will always be stable. So here you see that it explains why when you go from detached to attached, the stability is much better. So you cannot go to full power with that flame, but you can go with this one. Okay, so this is consistent with what we observed in the real gas turbine. Now, at that point, we started asking ourselves another question. If what we want is to have this flame, how do we go from that flame to this flame? How do you do that? Well, you can do many things. I would just show 2 things. One of the things you can imagine is to change the amount of pilot fuel that you inject here. You can split your fuel the way you want. You can put all the fuel in the pilot flames or all the fuel in the diagonal swirler, and you can change that. The other thing you can imagine also is that are those flames resistant to pulsation? Because if there is an acoustic forcing in this system, if you shake these flames, maybe you will quench that one into this one or vice versa. So this can be checked using LES. For example, you can define the ratio for the pilot fuel flow rate, saying it's the pilot fuel flow rate you have divided by the reference value. And we're going to increase that, and you're going to see the effect. And then we're going to add forcing to see what's happening. So here we start from the attached flame. And for the attached flame, we put more and more fuel in the line. And you see that when you put more fuel, you get extremely rich in this zone, and you actually get too rich. You get so rich that you actually quench the flame there, as you will see in a second. And now it's gone. So you can go from the attached to the detached flame if you put too much fuel. But that's not what we want. So we tried different things. And we built this diagram saying that if you are on the attached flame and you increase the pilot fuel, you put 4 times more than the nominal value, you will be able to detach the flame. But if you're on the detached flame, there's no way you can go back. There's no arrow pointing in this direction. So if you are detached, you can put as much fuel as you want in this zone, here and here. If you are detached, if this zone is cold, it will always remain cold. So the fuel flow rate cannot help you to do that. Now, there is another solution, which you see quite often in those burners, is that for another reason, if you change the regime or if you start developing an instability, then the flames will start oscillating. We went to very large levels of forcing, and I'm going to show you examples of what's happening to the flow here. So here we have the attached flame, and now we are pulsating strongly. And when I say strongly, you can see on the moving that it means strongly. Okay, you can see the flame moving quite a lot here. And so we're injecting waves. Let me go back. We are injecting waves here at the inlet. And you can see how these things are shaking. This strange shape that you see here on the equivalence ratio, it's because the flow is swirled and you have multiple veins. So here you see the fuel injected by the first vein, and here you have the wake of the second vein, the third vein, etc., etc. This is why you have this strange shape. The flow is shaking a lot when you start injecting these perturbations, but look at the stabilization points here and here. The flame always stays there. You can shake it very strongly. It doesn't want to go away. So that really means also that the attached flame is very resistant to oscillations. If it is attached, it's going to stay there. On the other hand, if you go to the detached flame now, you see we start from the detached flame. And you see here that things are a bit different. When you start shaking the flame, it starts flashing back here to this point. And then when it is there, according to the previous movie, it's not going to go away. In other words, if you start pulsating this flame, that's the same movie in a different view. When you start pulsating this flame, it's going to go back, and then it's going to stay there. Which also explains why in the real engine, if you at some point have, this is where things get a little bit complicated. If you suppose that you are stuck on this flame, but this flame we know is unstable. So what it's going to do is going to start a thermoacoustic mode, but when it does, it's going to shake itself so much that it will move to the attached case, and the attached case is stable. In other words, life is not so bad. If you have an unstable flame, this unstable flame itself is unable to survive to the oscillations that it's creating. So if it creates too much oscillation, it will go back to a stable case, which explains why you can operate the turbine. But still, it's a dangerous situation.
Forcing function is basically constituted but out of phase of the oscillation of the effect, or is it?
No, the forcing here, there's no phase needed. All the phase The phase here doesn't matter. You choose the phase because there is no excitation there. And when you start pulsating, you set the reference in time. You said, now I'm starting pulsating now, and that's all you need. Well, we go to 45% in 1 or 2 cycles. You know, it's really fast. So we just have this signal, then we go like this. There is no transition here. Yeah, for this case, everything is sinusoidal at the inlet. You could use other shapes, but we think that the result would be the same, okay?
And like when you are changing the forcing amplitude, so it is like a sudden change or you're casually changing?
No, we go, as I said, we just go very fast to the amplitude we want. So we have no forcing, and then we go to 45% in maybe 2 cycles. It's very fast. Only one. Here we force at only one frequency. It's F4. It's something like it's a confidential information. I can give it to you afterwards if you want that. It's a few hundred hertz, you know. So it means here that the bifurcation diagram is a little bit different. Now, if you are detached and you force sufficiently far, strongly, then you go back to attached. Okay. But when you are attached, you can force as much as you want. You always say attached, which explains in the chamber, which will be submitted to all kinds of forcing, that you end up with the attached state. Okay. So to conclude on that, in the same way that for non-reacting flows we have seen bifurcations, we also have bifurcations for the reacting flame. You talk to people at Ansaldo, I think Siemens has the same information. For this flow here, I've shown you 2 states, but there actually are 3 states. That's the attached flame here, and then when you look at when there's a detached flame, and then when you look at the attached flame, there's also 2 possibilities. So then they know for the same burner, they have 3 different flames. That's complicated. And remember, it's really due, we believe, to the swirler, okay? It's one of the drawbacks of using swirl. Swirl is good for flame stabilization. It's not good for complexity. It adds all kinds of complexities, and bifurcations are just one example. Okay, I have finished for this part. Any question on that one?
Where there is not just acoustics and peak interaction, there is hydrodynamic instability as well because of the pilot flame. So is that the case where you're showing the hydrodynamic instability is also because of gas turbine?
Well, this flow is full of hydrodynamic instability, okay? You have vortices everywhere. So yes, there is here you have thermoacoustics and vortices. You know, you can see vortices everywhere. So it's a clear case where hydrodynamics interact with thermoacoustics. Actually, the largest animal there in terms of hydrodynamics is the PVC. The PVC is really playing a big role in this business. Okay, so I'd like to, yeah. Here, the PVC is at something like 250 hertz or something like this. It's a few hundred hertz, not more, because it's a big turbine. Huh? I'd like to conclude now with, for this morning, with another example of things which may be wrong, or maybe a problem, let's say. If you start, I heard that you had quite a few big computers here on campus. So if you start doing a good and non-dissipative computation, you're going to hit this problem pretty soon. The first thing I want to mention is that, of course, every computer you use has limited precision. Okay, so you can go to a single, double, or quadruple precision, 10 to the minus 64, and even so you don't have infinite precision. So if you have finite precision, that means that you have rounding errors in your simulation. And it's not a problem if you have a dissipative algorithm or if you compute a laminar flow. But remember, turbulence is really amplifying perturbation. This is the butterfly effect. You know also this is the reason why we cannot compute the weather to more than 8 days. Why is that so? Well, it's because when you compute the weather, and you start from one initial condition, you get this kind of evolution. And if you change epsilon, a very small quantity in the initial condition, you go to another place. And this is called the divergence of trajectories in the turbulent space. And because the flow is turbulent, it's actually going to another place. So if you run your code, you're going to find different results. So you cannot say if it will be raining or not. Well, probably in Kanpur, you can say it for the next 2 months. But in general, it's very difficult. And so if these things happen in the real world, and if you get a good code, they must happen in your code. But when they happen on your code, then you start having problems. One of the problems is that rounding errors are not reproducible by definition, because they are rounding errors. And if you do a parallel computation, this becomes an additional problem. And the way we found this problem was that we were computing the same flow 2 times, and we didn't get the same result. So when one of my students computes things 2 times and doesn't have the same result, usually I start, hitting him, saying, it's your fault, you didn't do the same computation. But in practice, we proved that it was not. So what's the problem? The problem is the following. At each interface of a parallel code, it's one problem. There are many others, but at each interface here, this is core N, and this is another core. This is domain decomposition, so these guys handle these points, and this guy handle those points. And here at the center, we do additions coming from one side and from the other. So when we add things here, typically we add a contribution from that side, and then we add a contribution from this side. And if you've looked, at computer sciences a little bit, you know that addition has to be done carefully. And you know, for example, that addition is, of course, commutative. A plus B, then plus C is the same as A plus B plus C. Everyone knows that. But what people don't know is that the rounding error is not the same. Okay, the error on these numbers, if this is 10 to the power 7, and this is 10 to the power minus 10, and this is 10 to the power 15, depending on how you add these things, the error will not be the same. Now, in message passing, on most machines like this, you do not control the time at which the message will arrive. Because if you want to do the addition here, what you do is you call this processor and tell him, send me A, and then this guy, send me C, and then you add them. But maybe you will do A plus B, and then you will do C, because there were other users on this machine. But maybe you will do A plus B plus C if you get the message later here. Which really means that if you do a computation on a different number of processors, then you will have different results. It also even means that if you do the computation the same day with the same code on the same machine with the same number of processors, but your neighbor is using the machine also, so that it will change the order of the messages, then you will have a different result. And then you start saying, okay, this is nice, turbulence, blah, 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 but my code, if it gives different results when I rerun it many times, it's not a good idea. Because, of course, maybe it's doing that because of the butterfly effect, but maybe it's because this morning you have done a change in your code and you typed J instead of A, and it's just wrong. And then when you try to compare the simulation of this morning with the simulation of 1 month ago, one of the two is simply wrong, and you don't know. So let me give you the example where this started. We're just doing the test case that you have to do if you want to do LES, which is the channel flow. The channel flow, you have your wall here, you have a wall there, it's periodic in all directions. You add a source term in the pressure equation, you let this thing go. And so what I'm going to show you is a simulation where we start from this flow, from exactly the same initial condition, and then we let it go and we wait. And we do the simulation on 4 processors, and then we do it also on 8 processors. And then we wait. So this is what you see after 8 roll times. So that's the flow time, if you want. You see that this is the actual velocity. This is French, but I'm sure you understand actual velocity. If you look at the 2 flows, they look almost the same, okay? Look at, it's difficult for you to find a place where these 2 flows are different, because they started from the same initial condition with the same code, same subgrid models. But if you come back, a little bit later, 18 roll times, now you see that there are differences between these flows here. And if you come back 26 world times later, then these two flows start decorrelating, exactly like the weather would decorrelate, when you try to predict the weather. And now if you average those flows, so you take this flow, you average the velocities here like this, and since it's homogeneous, you can also average in planes and in time, and you do the computation and the comparison, you see that these two simulations have exactly the same mean velocity profile and the same IMS velocities. So it's the right flow. You're computing the right flow, but the instantaneous events are not the same, which is somehow consistent with the idea that since this flow is a turbulent amplifier, any difference will be amplified. In that case, the difference comes from the fact that here you have 8 processes, and here you have only 4. So that's changing a little bit, at each time step, the rounding error, and then this rounding error grows. Now, if you talk about things which grow, we can measure them by using a norm. We use 2 norms, actually. One norm is the difference of the 2 fields, the maximum of that, and then you can also look at the average differences, between the 2 fields. So U1 is the first simulation, and U2 is the second simulation. These simulations start exactly at the same point. The problem is how far do they go away from each other? Normally, if the ones would really be the same, these 2 norms should remain equal to 0 to machine accuracy. Machine accuracy here means, when we do, most codes are run in double precision, so machine accuracy will be 10 to the minus 15 or something like this. So when you plot these norms, you can look at one of the 2, they say the same thing. In a log scale, you see that they're actually increasing exponentially. So exactly like in the weather forecast, you have a very small difference between the 2 solutions, and with time, they go away from each other. Why do they reach a plateau here? Well, at some point, they get completely decorrelated. They have nothing in common. So the norm between 2 fields which have nothing in common is a constant. It cannot keep increasing. It's probably, if you do some mathematics, you will see that the norm of U1 minus U2 has to be less than the norm of U1 plus the norm of U2. So you cannot go to more than this quantity, which is where you reach a plateau. And you see that you start from machine accuracy here, and then it's growing all the time. And you cannot control that. That this is for the turbulent flow. So what we did then, we did the laminar case. If you do a laminar case, the flow now is not turbulent. Laminar case, you don't amplify rounding errors. So you'll stay there all the time. So it's really telling us that if you use a once code, you'll be here. You can run your once code 20 times, you'll have 20 times the same result. If you run your LES code 20 times, you'll have 20 times a different result. Now, it's even going to the point that we tried a different thing. There are ways in a parallel machine, there are ways to block the passage of messages. You can specify that you want for each one all messages to be taken in a given order and not in the order of when they arrive. That's slowing down the code a lot, but it really leads to a situation where the rounding errors are controlled. So we did that. In that case, we had no difference, and then we did something else. We just took the code and we changed 1 digit in the initial solution. So we went on 1 point here, basically in this flow here. The initial solution, we went here and we said the velocity of this point is the same plus 10 to the minus 16. Nothing, well, that's sufficient. Even a small quantity like this, if you look at these results here, this is the case where we have a different initial condition with just 1 digit, and you see that it's also growing exactly like what we had when we changed the number of processes. Even so now, the processes don't play a role anymore because we have neutralized the effects by forcing the order. So that's really telling you it's exactly the butterfly effect. 10 to the minus 16 on the initial solution, solutions change. Now, we also wondered, if maybe we're doing something with not enough precision. So let's say you should go to quadruple precision. So this is what we did. We used single precision, double precision, quadruple precision. You see, if you start from quadruple precision, you start from 10 to the minus 30 something, but you keep increasing exactly the same way. So it's not a problem of precision. You can never go to a machine with infinite precision anyway, so you will always have this problem. So if you have a good LES code and you run it like this, you will go to different solutions. Now, at that point also, we started saying, well, maybe it's a bad test case because it's a periodic case. You feel that if it's periodic, then any error which is created here will be fed back to the inlet, and that will amplify the problem. And so we said, okay, let's do a real case. And this is the real case here. So this is a swirler kind of configuration that you will compute to, and we just run it for a certain time, and we change just the number of processes. And you see that when you look at the velocity at one point, for a very long time, the two simulations here give exactly the same result. And then suddenly, poof, one of them goes away like this. And then, you know, if you're a PhD student and you're facing this problem, you usually just say, it doesn't look good, you know. So, and actually, it makes sense. If you look at the flow field, you see that after 80,000 iterations, this flow field is not exactly this one. Okay? It's just a little bit different. And if you do the difference between these two things, because it is an exponential growth, you have to realize that, of course, when the error, the difference between these two simulations goes like this in log scale, it really means that in physical scale, if you plot the difference between the two solutions, it's 0, and then suddenly it becomes very large, okay? Because it's growing exponentially. So this is why when you look at these curves here, you see that it's almost, the two solutions are the same until suddenly one of them goes away. But actually, they were different all the time. It's just that the difference between the two was growing slowly. And then suddenly, boom, it's exploding. So this thing is maybe a problem if you, for example, are looking at ignition problems or quenching, because if this would be a field of mixture fraction, and then at this point you would ignite, in one case you might ignite in a lean zone, and in the other case you might ignite in a rich zone, and then you would conclude that you had a simulation which started from the same point with the same code, and one of them will ignite and the other one will not. Okay? And which is actually what's happening. I will show you this afternoon. In many experiments, this is what's happening. You spark, does not ignite. You spark, does not ignite. And then suddenly you spark, hop, it ignites. Which is physics, you know. But it's disturbing if you write a code. Okay, so to conclude on that, it really means also that testing a code becomes difficult. The main problem you have when you write a code is to follow the code lines and make sure you did not introduce a bug. The way we do that is that we do, you know, retro test, if you want. We do a computation one day, then 2 months later we do it again, etc. At Surfax, we have an automatic program of tests with about 40 different test cases, and we run them every year, and it takes about 2 months. During 2 months, we do only that. We run the code on the previous test cases. Now, if the results change just because of that, when you run the code again, you don't find the same result as before. That's painful, because normally what we do is we look at the norm between the two solutions, and it should be equal to machine accuracy. So if you know this problem, it really means that you cannot do that anymore. And so, of course, then you can look at the mean values, but from a computer point of view, it's much better to look at the instantaneous flow fields. That you cannot do that anymore. And of course, the problem is that if you introduce a bug, it gives the same result. If you have a bug in your code now, the version of 2 months was good, the version of today is bad, you run the two, they are different, what do you conclude? You can say, oh, it's the butterfly effect. Well, okay. Let's say it's a weak excuse, okay? You cannot use it every day. But it's really a problem to maintain a code. That problem is there. You won't see it if you use once code. If you want to do LES, you will have to address this point. And again, you see, it's an interesting property of turbulent flows that these things happen, but you have to be aware of it, and you have to know that in your code you should see it. Okay, I'm done for this morning. Any question on that?
As you told, if you're running same case for different number of cores, you get different instantaneous
Yeah.
results, but the same mean.
Same mean,
will be
yeah.
the same. I tried this once, like for the flame transfer function, I'm getting different values for different number of cores. So it is not very different, but it is not the same. So what do I trust then?
For the flame transfer function, there's an additional problem. If the flow is turbulent, is that you need to average multiple cycles, not only one. Okay, I don't know how many cycles you do. You need to do, 5, 10 cycles. But then obviously there is also a random part in this process. If you do it many times, you will not find exactly the same transfer function, but it should be very close because it's an average quantity. So normally you shouldn't be too far.
It is not very far, but it is not the same.
Yeah, that makes sense again. Yeah.
So what do I trust then? The low number of cores because it has low rounding errors.
Yeah, that's difficult to say. Yeah, that's difficult to say.
So it is ideally you run it one core and you don't have any such interfaces which give you rounding errors.
Yeah.
That is the ideal solution.
There's no good answer to that. You have to. I would say the first thing really is to improve the number of cycles that you do, and normally this would average the rounding errors. Okay, if you run it too many cycles, you get to a steady, steady harmonic situation that should work. Shouldn't make a big difference. Other questions?
My question is related to yesterday's presentation on entropy wave. So why we are adding term wave with entropy, why not entropy fluctuation or something else? Why it is the entropy wave? Can we experience entropy wave in general like pressure waves?
Okay, it's not something I did here, but you know that if you take the Navier-Stokes equations and you linearize them, you can show that waves come in different families, and they are the acoustic waves. And the acoustic waves are associated to P prime and U prime. So you have a pressure wave like this, and U prime is like this, and they are asentropic. So P prime is equal to C square rho prime. So this is the acoustic waves. And they don't interact with entropy waves. Entropy waves, they are such that the temperature is going up and density is going down, so that you have exactly a constant pressure. So for entropy waves, there is no acoustic component. They live in different worlds. And if the amplitudes are small, these guys travel in the flow, and those guys travel in the flow. They don't talk to each other. They don't see each other. It's only in the nozzle, because of the acceleration, then suddenly this guy starts creating noise. Otherwise, from the Navier-Stokes equations, we know that these two types of waves are independent. Acoustic waves, entropy waves, they live separately. I'm not sure if that answers your question, but
Sir, can we experience entropy waves just like pressure wave? We are just experiencing pressure waves and
sure, an entropy wave is just a hot spot. Okay, it's if you have a zone where you have a high temperature locally with a low density, so that the pressure is constant. That's an entropy wave. The name entropy wave looks a little bit too complicated. We should call it a hot spot. It's a hot zone locally, and it doesn't make noise. There's no acoustic waves associated to entropy. That's exactly the way we do the demonstration. It's those things are independent waves in the linear regime for constant velocity.
if you try to make the combustor compact, make it more optimized, in that case I'm making the fuel more homogeneous. So does that mean I'm making my system more prone to combustion instability and it's generating more of acoustic and entropy waves?
Yeah, sure. That's what we said when we talk about entropy waves, is that when a combustor is long, the entropy waves are created here, but they are dissipated by mixing, which is much more efficient to kill them than acoustics. Acoustic waves travel a long time, but entropy waves is really a hot spot, and it will get diluted with the fresh gases, or even with the burn gases, and see if the chamber is long, by the time you reach here, entropy wave will be almost equal to 0. As soon as you make it shorter, you increase the possibility of having an entropy wave reflecting on the nozzle. So yes, when you make them shorter, you have entropy wave problems. But also, you cannot make them too short. You need to burn. You need to preserve the efficiency. Other questions? Okay, I think we're on time. We have to, Shantanu is not back, but we're supposed to make a picture. And then you have the soot session. And then at 2:30 probably we'll do the last session on ignition. And then we're done. Okay.